We leverage ARM heavily. We're not religious. We build x86 products too. But this talk is really about our experience with Ceph on ARM. And I know a huge number of OpenStack people use Ceph underneath. And if you really care about storage and you care about Ceph, you maybe care about this technical talk. So a little history about SoftIron. We were founded around 2012, pretty much around the sort of genesis of ARM64. We did a whole bunch of work in the early days around ARM, particularly doing software work for ARM under contract. We designed on virtually every piece of ARM64 silicon in the early days. We shipped the first production ARM64 server and did a whole bunch of stuff in that kind of early arena. We designed reference designs for certain companies like AMD, for example. And so we were sort of steeped in the early heritage of ARM64. We've been using it actively for 6 years. And we've had a very interesting journey, learned a lot, particularly around Ceph on ARM, obviously, but also just the results that can be got from using ARM64 in anger with Ceph. So, one of the things that I hear all the time around ARM is that, ARM somehow is magic. We know ARM is really good at certain things, particularly low power. You see it in mobile everywhere. It's kind of, almost universally dominant in tablets and phones. But it really is not magic. And the great irony of the ARM ecosystem is the instruction set and the cores are kind of the commodity, if you like, that you license from ARM. And what really defines the product is how you build the whole chip around it. And, if there is one icon that's important on this slide, it's really the central one, which is, around ARM, things, are built to a system on a chip. And it's very much a systemic approach to building a solution for one thing. And so often you'll see SoCs built around ARM64 that are very purposeful, very focused on certain verticals. And when you come to storage, you can find SoCs that do an amazing job in storage. And what we found is that there are different parts of the ecosystem within storage. Certainly within Ceph, there are different roles and different activities. And for the bulk of the storage, the OSD nodes that do the storage of all of the data in Ceph, ARM is just an absolute match made in heaven. And so, I'll not waffle on about how good it is. I'll just, say the thing that our CEO says all the time, which is the only thing that matters in the world are results. And so this is an interesting graph. We can just leave this up all day because I love this graph. Basically, it's a graph that a customer created. It's not our data, it's customer data. It's a comparison of Ceph running on our lowest performing box against a dual Xeon E5, many dual Xeon E5s in a cluster. And the lower performance on the graph is the x86 OSD nodes, and the green graph at the top is SoftIron hyperdrive results. So, one of the things that we do in creating products is we obviously tune them highly to run Ceph. Every product that we create is wire speed, i.e. it will fill the pipe. And, the results are kind of, there's no hiding behind anything. This is customer data. Another thing you'll see on the graph too is that the green graph is smooth, which is a reflection of an I/O path result, as opposed to the more jagged line, which represents and explains some of the internals of what's going on and why those performance results are weaker on a processor that really is sort of top end of town. It's the graph really shouldn't occur in nature, but it does. So there's something going on here that's really interesting around ARM64 and Ceph. The question is really what is the thing that's really going on? So we'll delve into a little bit of that. So basically, if you look at a storage product one way, one kind of mental way of looking at it is that it's really a processing path that involves Ethernet or network media on one end and storage or media on the other end. And so what really controls obviously the performance of the product is just the velocity of bytes. And the dirty little secret around, I think most, but certainly on Ceph, software-defined storage in general is it's not really bound in software. So it's an irony of software-defined storage. Really the thing that controls the performance and allows us to get the graph that I just showed you is the fact that the path through the silicon is very highly optimized. So getting things from and to Ethernet, getting things from and to storage media is full of subtleties, and those subtleties add up and add up. Ceph is a very complicated piece of code. It's, like a human organism, it's very, very complicated, and it's very sensitive to, these silicon paths, this optimization that is possible with a system-on-a-chip approach, as opposed to a generic processor approach. And some of the reasons why are things like I/O channels. When the chips are created, often you have many, many dedicated I/O channels that are peers, they're not tiered. Often when you see a generic processor, you'll see tiers of I/O, different classes, different speeds. Sometimes it's laid out in a topology that has wait states or bridges or things that get in the way. All of those add up to have a bigger high-level effect in Ceph. And one of the things that we leverage in a system-on-a-chip architecture that is so easy, both on the Ethernet or network side and the media storage side, is direct memory access, or the DMA. And so if you can do DMA and leverage the silicon paths, you do not need to burn processing power. And so your dependency in software-defined storage is not waiting and leaning on the software side. So the processing power is really, you want to have enough, but beyond enough, it's really just kind of a waste. And it really isn't the thing that controls the performance. This is one of the things we learned. And so in creating an ARM64 chip, like I said, very much the ARM64 part is a commodity that you license from ARM. You can buy it as a core, you can buy it as an instruction set, but it's kind of a thing. You use it for the processing, but it's really the chef's choice. So when you decide to kind of bake a processor based on licensing ARM cores, you have to surround it with peripherals. Those peripherals are generally I/O, Ethernet, SATA, SAS, PCIe, whatever your connectivity is. And depending on what that SoC is being built for, it could be very applicable for certain things like storage, or it could be very applicable and focused on things like generic processing. It could be focused on networking. And so if you look across the landscape of ARM64 servers, and you can find the right one that does storage extremely well, then you'll get the results that we're getting. And so that's one of the things that we learned. Another thing that we learned, and it was very interesting, is just what opportunity there is to port to ARM for performance and for all sorts of other quality metrics in Ceph. Often porting to ARM means that you type make, and at some point it says build successful, and that's just the price of entry. You just started. There's a lot of opportunity inside ARM for optimization. So one of them, some people see ARM and say, well, there are things like single instruction, multiple data, DSP and optimization paths. Neon is the term of art in the ARM ecosystem. There are instruction path optimizations, there are compiler optimizations, there are data handling and sequencing opportunities, all of which we did and explored into an effect by doing not just porting to ARM the build successful stage, but actually doing the optimization. You can get an uplift in performance of around 25 to 30%. So very, very significant optimization in targeting ARM. Ceph is a big, complicated code base, and so there's a lot to chew at there. The other thing to note is that the entire stack of software is really important. So on an SoC, you typically have firmware that runs on the chip below everything else that boots. We got massive performance uplift on firmware optimizations beyond the standard kind of release of firmware that comes from the chip vendor. That's a kind of dark and mysterious art delving down in those, that plumbing. There are optimizations also in UEFI that are often, UEFI is often very generic. It's booting a PC, it's booting whatever it is, and the UEFI doesn't care if it's a processing load, a database load, a storage load. Well, we know we only make storage products. So we can optimize UEFI and firmware for that very thing. The same with the kernel, the same with drivers, the same with peripheral handling, the same with I/O operations, all again with this back tapestry of porting it specifically for ARM. And then there are optimizations in Ceph as well, which I mentioned, but also in leaning out the distribution. So if you know that you have just Ceph being served by the OS, everywhere in the OS you can make all sorts of optimizations, mostly about being lean and not having other dependencies around that will slow things down. So very much a targeted approach. So one of the things that ARM is known to be very good at is low power. And when you make a storage product, one of the chief enemies, and it's always an incumbent, is heat. And so just, if you compare, say, for example, x86 with ARM64, and, being polite to our venue, we do x86 stuff too. But the ARM64, it's just the laws of physics. An x86 processor generally, with all the kind of caveats in the room, will never be as low power as ARM64 just because of the number of transistors that you move around. And so you may be a criminal, you don't have to obey the law, but the laws that you do have to obey are the laws of physics, they're sort of mandatory. And so, one of the things that happens is heat begets heat. So as processors get hotter, they use more and more power. As they use more and more power, they produce more and more heat, and that can be a thermal runaway, but it's just a thing that happens. And so anytime you have heat, it's like the gift that keeps on giving. You pay for the power, the electric, you have an electric bill, and for every bit of electric you use, the gift that keeps on giving is you get to pay for the electric bill for the AC to get rid of the heat it produced. And so, if you can remove heat, there are all sorts of secondary effects that happen other than just OPEX reduction, which at some point can even pay for the CAPEX of the product. And so there is this vicious circle. One of the secondary effects that happens with heat, particularly in a storage product, is the longevity and reliability, if you like, the quality of the storage, is highly related to temperature. And so, in physics, we know that for every 10 degrees C of increase in temperature, you'll double any chemical rate reaction. Again, another law of physics. But how that relates to MTBF is that for just, say, 20 degrees or 25 degrees, typically is the difference, in our product versus a standard PC, you will see a doubling or a halving of the lifetime, depending on if you're reducing or increasing heat. So we're really focused on reduction of heat. Because ARM is so low power, one of the things we can do is control the airflow. So we can actually run the airflow over the thing you care in a storage product most, which is the storage media. You couldn't do that in a traditional environment when you have half a kilowatt or a kilowatt of compute that really is just there to serve the connectivity to the storage media. And so we can basically double the life of the storage media. It's not very exciting to my mum. She barely understands it and certainly doesn't care. But if you're the guy at 3 o'clock in the morning that has to go to the data center to pull drives and replace it, you really care. If you're the CFO, you probably also care about doubling the lifetime. So that was all based on manufacturers' data, Seagate and HGST in particular. It's relevant for both, spinning Rust as well as for Flash for different reasons. Happy to talk about the details after if you like. So basically, this is kind of rather a judgmental slide, if you like, but, power is just a waste. It creates heat. Heat is reliability as well as cost, and it also relates to what you can fit in a box in terms of density and performance. So, that's just kind of a lack of imagination, but it's kind of incumbent when you start with sort of more generic hardware that may be doing anything as opposed to dedicated to storage. And so we learn that. And so, I love this picture also because a picture's worth 1,000 words, and if you look at the difference just in, a thermal picture like this, you can see we found the lowest power x86 storage product we could, which is made by Supermicro. It's not really important, but it's a standard PC. It has 10 drives in the front, which you can see it's on the right-hand side of the diagram here. And then you see a whole bunch of heat. You see a difference in comparison with the heat of the drives, as well as, the whole ecosystem of what is essentially a processor chipset. So, this collection of things here, that's all a chipset mentality as opposed to an SoC mentality. So there's multiple pieces of silicon that are all baking and getting hot. If you look over here, this is our processor, not the red bit, but the blue bit. It's really cold. We only need one fan, so we have a lot of backups. You see one fan really cold there. Hotter because it's producing heat. Fans actually produce about 7 to 10 watts of heat, so every piece of cooling that you need because of that actually just adds to the whole problem of thermals and heat and power and reliability. And we can see here that, like, in our box, the highest power thing is the thing that we don't make. We make everything else, but that's actually an M.2 drive. So incredibly cool, and that's how we get the reliability uplift and everything else. And so if you guys don't have any questions, I was going to delve into a few things that we've, based on what we've learned, what we're going to try and do in the future. And so one of the things that we know about Ceph is that it likes to be horizontal. It loves to scale out horizontally and behaves and scales in both performance and all of its other properties, in that you double the number of boxes, you roughly double the performance, you certainly reduce the failure domain. Everything basically gets better in Ceph as you scale horizontally. And based on what we learned about how low power we can make things on ARM64 and get the performance uplift, one of the opportunities is we're not limited on cooling, we're not limited on density. It's very compact in comparison. It's an SoC versus a chipset. So both in terms of physical mass, power delivery, power in the whole rack scale, and just heat extraction inside the box, we can fit multiple processors. So we can do something that would make a terrible computer. Instead of having, if you were designing a computer, you wouldn't want separate islands of compute. But that's exactly what Ceph wants to do. So with some networking magic and some other caveats and some secret sauce, we're basically producing multiprocessor designs now that will uplift that performance graph by 2 and 4 and more. And so we think we can make boxes that approach a petabyte with 100 gig of wire speed performance. So one of the other things that we're looking at and doing and kind of collaborating in the Ceph community is venturing out and using customized hardware to build what we describe as a storage utopia. So the idea is that you can use erasure encoding, which gives you the moral equivalent mathematically of 3 copies of data, say, which is what enterprise is comfortable with in terms of replication. So use that mathematical alternative to replication, do erasure encoding, which gives you the resilience and reliability. It also accelerates writes. So if you don't have to write 3 copies of the data, you're faster. Generally, though, you're going to pay for it in reads, because when you read, you need to do calculations to recover the data from the erasure encoding, the format it's stored. And so we think we can do that in hardware. We have kind of a working prototype at this stage that allows us to pay no penalty for erasure encoding, which means you only have to use 1.3 times the data footprint of a byte of data to store it. We think we can do that at wire speed with no penalty for erasure encoding. And we can also do inline compression at wire speed. So you'll get the moral equivalent of 3 replications. It'll run at wire speed for all Ethernet speeds up to 100 gig. And you'll use 1 byte of data in storage for 1 byte of usable data in user application land. So we're pretty excited about that. And then, if you afford me an advert, we're hiring. We're a startup company. We're growing like crazy and doing some good stuff. And if anyone's interested in talking after, we'll be around. Say again, sorry?
What is your customer base? Who needs this?
I mean, basically anyone that's using Ceph at some level. We find customers that, for example, have rack level limits. So, some customers, they basically have a 10 kilowatt total rack limit on power, and they have they're basically renting thin air in data centers at some level. They put 5, 10 boxes into a rack, and they go, well, we can't fill the rack. So that's one area that we do well. People that are doing things at scale often really care, and because we're very, very dense in comparison. And we do well whenever anyone says the word performance. So generally, our performance is kind of you saw on the graph like a 2 times uplift from a traditional kind of topology or technology, and so we have a 2 times performance uplift. So density, and then just cost. The OpEx variation can often pay for the product itself within just a few years. So if people are cost sensitive, performance sensitive, power sensitive, heat sensitive, work in environments where maybe you don't have air conditioning, kind of edge cases and things. Various different reasons, but there's kind of something for everyone there, and doing it a little bit differently around ARM64. So people care for different reasons.
Any plans to move beyond Ceph, or is it going to be Ceph forever?
We're really aware of things other than Ceph, and our box is really, like I said in the presentation, our box is really optimized for I/O. So, the reason that Ceph runs really well is, well, we're very focused on that, number one, so that's what we do. But, anything that is storage, I mean, really it boils down to how well can you get things at some level on which you care about performance from Ethernet to storage and storage to Ethernet. If you really care about things like quality or reliability of data, the same thing is true. It's just physics. You know, you have less heat, it's more reliable. So if it were running Gluster or BGFS or any other kind of workload, it would perform the same way. And we validated that, we know that. So that's the thing that we're kind of looking at. So if you want to be specific later or something, we could have a chat about that.
What's the preferred storage media? I mean, are people still using rotating spindles? Do you guys care? Are you supporting it all?
Yeah, we're sort of agnostic. I mean, we do spinning rust, we do flash, we do all of the technologies. I mean, one of the things I didn't talk about here, because it would sound like an advert, is we have a technology platform that we build everything on. And so we're kind of insulated from whatever it is. It can be NVMe, it can be SATA, it can be SAS, it can be spinning media, 3.5, 2.5, we don't care. And so we have products that are very focused on value, that leverage ARM in that way. And so that's spinning media primarily. We have a thing that we do, because ARM64 allows us to do that, where we have this really weird hybrid way of doing things, where we try to get flash-like performance for a short period of time relative to infinity by backing flash with spinning media. So that's one thing we do, and we can do that really well with the multiprocessor stuff we're about to do. And then we have just pure raw, we're known for performance, so like that leads you to flash, and so we have all pure flash products. So we really don't care, and we take the same approach to processing actually, which is how we got to ARM64 for OSDs. We take the same approach for networking, so we don't care how you want to do the networking. I mean, it can be Ethernet, it can be something else. We do all of the speeds, we do all of the media, everything. So we try to be agnostic about all of the things that are sort of incumbent for a customer. We're just very focused on what those customers want. Anyone else? Any more for any more? Do you want me to bring your laptop back now, Jason? Okay, guys, thanks a lot.